Good morning, everyone. So, in the last class, we talked about the different classes of the graphs, mainly path graph, cycle graph, and complete graph. Today, we'll discuss one more important class of the graph, which is regular graphs. So, let us consider that there is a collection of guests at a party, and some guests shake hands with the other guest. If we asked everyone at the party how many guests they shake hands with and added all those numbers, then what would be the sum? Think over it. Let's say there are 10 guests. The first one shake hand with 5 people, the second one shake hand with 3, the third one with 7, any random numbers. Of course, they cannot shake hand with 12 people because there are only 10 people in the party. So anyone can shake hand with at most 9 people. Yes. After shaking hand, if we add all these numbers, then this sum would be equal to twice the number of total handshakes. So we will prove this result using graph theory or by modeling the problem using graphs. The next question is that is it possible that every two of them know a different number of the people in the group? So let's say 10 people are there. We are asking that each one can shake hand with at most 9 people. So is it possible that everyone shake hand with the different number of the peoples? Again, we will answer it using graph theory. So degree of a vertex is the number of the edges that are incident to the graph. The number of the edges that are incident to the vertex. One important observation is a loop contributes 2 to a vertex degree. Let's see an example. So we can see here that degree of u1, because 3 edges are incident to it, so it's 3. u2 it's 2. For u3 there are 4 edges incident to it, and u4 you can see this is 1 edge, but loop is contributing 2, so this degree is 3. So this is how we compute the degree of a vertex in the graph. So this is the first theorem of graph theory, handshaking theorem, which says that the sum of the degrees, this is representing the sum of degrees of all vertices, is twice the number of edges. Why is it so? Let's first verify it. So we have already seen this one where we computed the degrees. Now sum of the degrees is 12 and the edges are 6. You can count the edges. And you can see that sum of the degrees is twice the number of the edges. Why is it so? To understand it, let's label the edges. 6 edges are there. So when I am counting the sum of the degrees, I start with u1. So for u1, these edges e1, e2, e3 are contributing to its degree. For u2, e1, e4 and so on. If you add all them, it comes out to be 2 times e1 plus e2 and goes till e6. This is because each edge is contributing twice to the degree. e5 is also counted when we are computing the degree of u3, and it is also counted when we are computing the degree of u4. And this is why this sum of the degrees comes out to be twice the number of edges. So important remark that in any graph there is always an even number of vertices having odd degree. So this is because degree sum is always an even number. This is twice the number of the edges. So degree sum is even number. If there are odd vertices with odd degree, then degree sum would become odd, which is not possible. And this is why in any graph there is always, you can try to draw any graph by yourself randomly. You can see that this degree is 3, degree is 3, this is 2, this is 1, this is 1. So there are even number of the vertices, there are 4 vertices with odd degree. So we say that a graph is regular if degree of each of its vertex is equal. So you can try to draw the graph. Let's say I draw this graph. So this is regular. Sorry, this is not regular. This is 3, 3, 2, 2. I have to make them adjacent. So 3, 3. So this graph is regular because degree of each of the vertex is equal. A graph is 3 regular if degree of each vertex is 3. So here degree of each vertex is 3 and therefore it is 3 regular. So for null, cycle and complete graph, find k if there are k regular. Please do try it by yourself. You will see that all of them are k regular. The null graph is 0 regular because it has no edges. Cycle graph is 2 regular, and the complete graph kn, where each vertex is adjacent to all the remaining vertex, is n minus 1 regular. Each one is having degree n minus 1. And the complete bipartite graph, it is regular only if m is equal to n. For example, if I write k 3 3, then it is 3 regular. But if I write k 2 4, then it is not regular. So you can try to draw k 3 3, and you can see that each one has degree 3. But if you draw k 2 4, so each one is, this is k 2 4. So you can say that it is not regular. Compute the number of edges in k regular graph on n vertices and in complete graph. So again we'll use the degree sum formula. We know that the graph is k regular. It means degree of each of the vertex is k. So if I found the sum of the degrees, it should be kn, which is twice the number of the edges, and therefore the number of edges are kn by 2. Now in complete graph for kn, we have this small k is equal to n minus 1, and therefore the number of edges are n minus 1 by 2. Please do remember this result, that in the complete graph the number of edges are n minus 1 by 2. So let's move to the next question. Every vertex of a graph of order 14 and size 25 has degree 3 or 5. How many vertices of degree 3 does this graph has? So order is 14 and we need to find the vertices of degree 3. Let's assume that the vertex of degree 3 are x. It means all the remaining vertices are of degree 5, and remaining vertices are 14 minus 5. Now using the degree sum formula, 3x plus 5 times 14 minus x is equal to twice the number of edges, which is 50. So 3x minus 5x, which is minus 2x, and 50 minus 70, which is minus 20. This implies that x is equal to 10, which means that there are 10 vertices of degree 3. Describe all one regular simple graphs. So one regular simple graphs, these are one regular simple graphs. Please do try to solve each question by yourself. It means these are disjoint union of P2. And similarly, two regular graphs are disjoint union of cycles. There could be any cycles. For example, these are also two regular graphs. A graph, it's a cycle itself is a two regular graph, and so on. Show that a simple graph on odd number of the vertices cannot be three regular. We have already discussed it. Because the number of the vertices are odd and it's three regular, then the sum of the degrees is 3k, where k is odd. It implies that 3k itself is odd, but degree sum is always even, therefore it is not possible. And for every even n, there is a three regular simple graph on n vertices. So this part we are going to prove it by construction. In this course, we will see that we can prove a result by contradiction, by construction, by induction, and many more ways. So this is the result. By construction, we mean that we need to construct a graph, or we need to tell a method to construct a graph for any given number of the vertices. So let us assume that I have to construct a graph with 2n vertices. So what I do, I call n vertices u1, u2, un, and the other vertices as v1, v2, vn. Then I draw a cycle with u1, u2, un and v1, v2, vn, and then make each ui adjacent to vi. This gives me a three regular graph. So I gave you a methodology to construct a three regular graph with even number of the vertices. So this is a proof by construction. Is there a simple graph on n vertices such that the vertices all have distinct degrees? So the answer is no, because the degrees can be 0, 1, 2 and the maximum degrees n minus 1 in a simple graph. Now if the degree is n minus 1, it means it is adjacent to all the vertices, which means all the remaining vertices in the simple graph has at least degree 1. So degree 0 is not possible. And this is why we cannot have all the vertices having distinct degrees. But if we consider a general graph, it is always possible by introducing loops and multiple edges. Consider a simple graph of order 7 and size 10 having 6 vertices of degree A. So 6A and plus B is equal to 20. We need to find B and then find A and draw the required graph. Now there are various values of A and B which satisfy this equation, but we need to see that for these values does there exist a graph or not. Let's see the example. So A can be 0 and B can be 20. So it is not possible that you could have 6 vertices of degree 0 and 1 vertex of degree 20, the graph of order 7 and size 10. Similarly, 114 and 28 are not possible. Please do try by yourself. And you can see that the only possibility is A is equal to 3 and B is equal to 2. And this is the required graph where you can see that there are 6 vertices of degree 3 and 1 vertex of degree 2. Next is degree sequence. So consider a graph G, then a sequence of the degrees is the degree sequence. But for convenience, we always assume that this degree sequence is non-increasing. Let's see an example. So for this graph, the degree sequence is 3, 3, 2, 1, 1, 0, where 0 is the minimum degree and 3 is the maximum degree. The notations for minimum degree and maximum degree, small delta g and large delta g, please do remember them. Now we say that a sequence of non-negative integer is graphical if it is a degree sequence of some simple graph. For example, if I write down this sequence 1 1 1 1, then I say that it is graphical because there exists a simple graph corresponding to this one. But if I write 1 comma 0, so you cannot draw a graph with two vertices where one vertex have degree 1 and the other vertex have degree 0. So this one is graphical, but this one is not graphical. Now, how do we know if the sequence is graphical or not? Especially if the sequence is large enough. So to identify the sequence is graphical, we will discuss Howell-Hakimi theorem. It says that let S be the given sequence d1, d2 till dp, and S1 is the sequence which is obtained by deleting d1. So you can see that d1 is not here, and then subtracting 1 from next d1 terms. And then we say that S is graphical if and only if S1 is graphical. We are not discussing the proof of this theorem, but if you are interested, you can find, it's a well-known proof, you can find in any of the book. So using Howell-Hakimi theorem, let's try to check if the given degree sequence is graphical. So to check this one, what has been done is that this is the procedure. You compute S1, and how do you compute S1? You delete the first term and subtract 1 from the next 4 terms, because this is d1 is equal to 4. So first 4 terms, which means minus 1, minus 1, minus 1, minus 1, and this remains 2 only. So S1 becomes 3, 2, 2, 1 and 2. Now you reorder S1 because you want non-increasing degree sequence. So 3, 2, 2, 2, 1. Again you delete the first term to have S2, and then in the remaining 3 terms, because D1 is 3 now, you subtract 1. So you will have then S3, you delete the first term, and then in the remaining 1 term, this is the term, you subtract 1 and you reorder it. This is S3, and S4 is you delete this, and in the next term you subtract 1, so 0 0. Now 0 0 is graphical, and therefore it implies that the given sequence S is graphical. Let's try one more question. So in that case, again S1 is, you delete the first term, and from the next 5 terms you subtract 1. So 3, 2, 1, 0, 0. For S2, delete 3, and then the next 3 terms you subtract 1. 1, 0, minus 1, 0. Now we know that S2 is not graphical because we cannot have a simple graph or any graph having negative degrees. So this is not graphical, and this implies that S is not graphical. So if we talk of the algorithm which we have already discussed, so for any given sequence, if all di are 0, it is graphical. If any of the di is negative, it is not graphical. So we always reorder s to a non-increasing sequence, then delete the first number and from this delete the first number from the sequence and subtract 1 from the next n numbers and keep repeating it. So this is what we have done. At the same time, it's interesting to observe that using Howell-Hakimi theorem, we can have a graph for the given degree sequence if it is graphical. Let's see how, or you can try to think by yourself first. So we have already proved that this sequence is graphical. And to prove it graphical, these were the steps. We started with S, moved to S1, then S2, then S3, and then S4. Now once we have S4, then I can go back, because I identified that S4 is graphical. Now what does S4 represent? Two vertex with degree 0. Now from S4 when I move to S3, 0 remains 0. So this 0 remains 0, I can say. 1 of the 0 becomes 1 and there comes a new vertex with degree 1. So new vertex with degree 1. So this is 1 1. Now the isolated vertex 0 becomes 1. These two remains as it is and new vertex came with degree 1. Now again all these three ones, any of the three ones becomes 2. It means the new vertex is adjacent to three existing vertex of degree 1. So I can make it adjacent to three existing vertex of degree 1. And then the last one, degree 4, it means it is adjacent to 4 vertices, 2 remains 2. So it means it is adjacent to all other vertices other than a vertex of degree 2. Now there are many choices. This is also a vertex of degree 2, this is also a vertex of degree 2, this is also a vertex of degree 2. You can leave any one of the vertex with degree 2, and which shows that the representation is not unique. So this is the last one, you make it adjacent here, here, here and here. And now you can observe that this is 4, this is 4, this is 3, this is 3, this is 2, this is 2, which is the required graph corresponding to the given degree sequence, but the representation is not unique, which can be observed from this example also. So degree sequence for both the graphs are 3 3 3 3 and 2 2 2 2. But in the first case you can see that the 4 vertices with degree 3, they forms a cycle of length 4. But in the other graph, the 4 vertices of degree 3, they are not forming a cycle of length 4. They have the different properties and therefore the graphs are distinct. It means that if the two graphs have the same degree sequence, we cannot claim that the graphs are same. So in the next class, we introduce the concept of subgraphs. Thank you for watching.